top, you see Registered Continuing Education Program. The feedback that we'd gotten from previous webinars was, could we offer professional development hours? And we are in the process of getting certified through the Registered Continuing Education Program. And so today's webinar is going to be structured a little bit different than the ones I did before, because we are trying to get this certification for that. And then we will be able to offer people professional development hours. So one of the things that they require is at the beginning, we talk about what the learning objectives are. So this class, we're going to talk about how to perform sag and tension calculations, and we're going to talk about them in the context of the two most commonly used software platforms, which are Powerline Systems PLS CAD and Southwire's SAG-10 program. We're going to talk extensively about the meaning and importance of the maximum rated design tension and how that should be used in sag and tension calculations. We're also going to talk about real lengths, why they're important and how to come up with them. Closely related to real lengths is doing splice point location, so we're going to talk about that. And then we're going to close with just a couple tips on things that you should include in your purchase order to help ensure that the project logistics go smoothly. So let's get going. Oh, I almost forgot to mention. After the webinar, we will be sending out a test for everybody who participated. Now, if you don't want to take the test, just don't take the test. But when we're certified, you would have to take the test and you have to score 70% in order to get credit for the professional development hour that you would earn. So now let's get going. Okay. So first up, sag and tension. The first thing that you need to do is to figure out your loading criteria. And that starts with what is your base loading criteria. Now, let me take a little bit of an aside. I know I have some international participants in this webinar, and I'm sorry that I'm talking about it very from an American point of view. You should be able to take the concepts that I talk about and apply it to your country. So we begin, your country may have base loading criteria. In the United States, we have 3 base loading criteria. We have heavy loading zones and medium loading zone and a light loading zone. In addition, there are state requirements as well. California has something different and Hawaii has something different. So you begin with your base loading criteria. In the United States, that's NESC Rule 250B loading criteria. Now, that loading criteria goes back decades. Within my lifetime, you see NESC Rule 250C and D, which add extreme ice or concurrent wind and ice conditions. So those are kind of on top of it. And again, your state or your country may have additional requirements as well. So you need to gather all of those together. On top of that, you might even have some tension limits that are unique to your utility or perhaps to a specific project. For example, sometimes when people are replacing a conventional ground wire like a 3/8 inch EHS, they may want to limit the tension. A common tension limit that I see is 5,000 pounds. So whatever tension limits, or you might have some specific sag limits, whatever those are, you need to collect all of those together. That's got to go into your program. Next, you need to get your cable specifications ready. I mentioned that we're going to be talking about the 2 most commonly used programs, which are PLS CAD and SAG-10. And both of them are actually very similar, and the base data that they need is exactly the same. And that is the cross-sectional area, which is going to be given in square inches or square millimeters, the outside diameter in inches or millimeters, the unit weight, pounds per foot or kilograms per kilometer, and the rated breaking strength, which can be pounds or kilonewtons. You find this information on the cable data sheet. If something's missing or you don't have the cable data sheet, then you should ask the cable manufacturer. They can easily provide it for you. Now, it's very important, and if you take away only one thing from today's webinar, this should be it. You need to know the maximum rated design tension, and that is defined in the IEEE standard 1138. It's basically the tension your design should never, ever exceed under any loading condition. So it doesn't matter if your utility is looking at a 1 mile an hour wind or a 180 mile an hour wind, the tension under that condition cannot exceed the cable's maximum rated design tension. Likewise, it doesn't matter if you're looking at no ice or 5 inches of ice. The tension on the cable under that condition cannot exceed the cable's maximum rated design tension. Now, this is the official term that was adopted by the IEEE. I believe it was the 2009 edition. This term is also known as the maximum rated cable load, or MRCL, but the meaning is exactly the same and the effect is exactly the same. Now, we're going to talk about PLS CAD and sag tension separately because they take a slightly different approach into how you set up the problem file to do your sag and tension calculations. I'm going to start with PLS CAD first. We'll go through what goes into PLS CAD, and then we'll talk about sag 10. Now, with PLS CAD, you use what's called a wire file. A lot of times people will type it out as wire, W-I-R-E, but officially it's a file that ends in .wir, hence the name wire file. And I'm going to show you how to set up your own wire file because you ought to have a basic understanding of what's in the wire file and how to do that. But I'm going to hit it pretty fast in the interest of time, and I'm not going to dwell on it because quite frankly, you should just get one from the cable manufacturer. Any cable manufacturer should be able to send you a wire file for their cable that you're designing with. In addition, if you on Powerline Systems website, they actually have a library of cables with wire files for them. You can go on there, you can find in-cab and you can find other OPGW manufacturers, and they may not have every single cable that the manufacturer has, but you should find a good library and you got a good chance of finding the wire file for the cable. But of course, as I say, you can go to the cable manufacturer and ask them for a wire file as well. So a wire file is actually a text file, and it has a certain structure to it that the program is expecting when you load it into the program. What you see here is a typical wire file, and this first line, actually the first 2 lines are just text data. They're not actually used by the program for calculating anything. At in-cab, what we do is the file name is equal to the cable designation plus the sag tension chart that's used, and I'll explain why later. The second line is just reference information. Again, we repeat the cable designation, and then there's some basic information about the cable. This is the overall diameter, the maximum fiber count you could get in this design, the fault current rating at a maximum temperature. The assumed starting point is 40 degrees C by way. And then just some comment that it was one that we developed and the date that it was done. This information is all strictly for reference. What's the program is really using are these numbers here and these numbers down here, and we'll talk about them in turn. So first you have the cross-sectional area, the diameter of the cable, the unit weight, and the rated breaking strength. This line is another text line that appears, and it's 100% consistent among manufacturers, I always put in the sag tension chart number, and I always put in that number, the maximum rated design tension. Those are there just for your reference so that you know that that what follows is chart number 1-1441. These numbers are sag-10 chart coefficients. And we'll talk about exactly what they are on the next slide. Then you come down to some more text here. And then the last line is the resistance that you and some data that you use for steady state and capacity calculations, which is very different than fault current capacity calculations that you use for OPGW. So this information is not really relevant for OPGW, and usually it's left blank. These values here are the resistance, and then this is some special values, and then the values that the resistance are at, or excuse me, the temperatures the resistance is at. And it's usually just zeroed out, except for the default values here. Okay, so that chart number you'll find on the manufacturer's cable data sheet. So this is a typical one for us, and here's the chart number that goes with this specific cable design. But anybody's cable design or any other manufacturer's cable data sheet should have the sag tension chart number on it somewhere. And if not, that means they're probably not experienced in the US market, and you'll have to ask them for it. Now, I mentioned those coefficients in the chart, and I said I would explain what they mean, and this is the slide to do that. So this first line are stress-strain polynomial coefficients, and you can see 1, 2, 3, 4, 5 separate numbers. So that means you've got a fourth order polynomial coefficient, and what it's doing is it's describing the stress-strain behavior of the cable. If you went and did a test and plotted the results, you would get something that looks like this. The second line is the creep polynomial coefficients. That gives you this line. Then you end up with a line with just one number on it. That's the modulus. And then another line with just one number on it, and that's the coefficient of thermal expansion. Now, then these are repeated in form. For most OPGW sag-10 charts, these lines will be zeroed out. And what that's telling you is that the cable's being treated as a composite cable, not the aluminum separated from the steel. So on my little chart over here, what you see, the numbers that I was showing you before, or the curve I was showing you before, this are the stress strain coefficients of the aluminum. Somewhere in here, where you read it, are the stress strain coefficients of the steel. And this is a practice that was done decades ago for ACSR conductor. The aluminum information was separate from the steel information. But for OPGW, what's been much more common has been to treat the cable as a composite. So all the data that's relevant to the OPGW is just in the first 4 lines. And on my graph over here, you can see a composite cable is here. And with that ACSR conductor, if you took the aluminum and the steel, took the aluminum and the steel and put them together, you would get a curve like that. And then the last line is the test temperature. So when they were doing the testing to get these coefficients, or excuse me, technically to get the data in order to calculate the coefficients, this was the temperature that they did the testing at. Now, when you're working with PLS CAD, it is much better to start with a wire file for a cable that uses the same chart number as the cable you're now working with. So it's another cable design, completely different, except for the fact that they share the same chart number. That's what we call a donor file. And if you don't use a donor file, then you would have to type in all of this text data by hand. And that, as I note here, would be at best tedious. And if you get one of these numbers wrong, you risk having incorrect sag and tension calculations, and that would be bad. So I never start from scratch with PLS CAD. I always start with a donor file. How you do that is to open an existing wire file by right-clicking on it. And I prefer to use Open With and use Notepad. Now, by default, what most Windows machines are going to do is open it with Word. And the problem with that is that if you aren't really, really careful when you finish editing it and save it, Word's going to change the format to a Word document format instead of a text file. And then the file won't open from PLS CAD, and you'll be wondering why, and it'll be a mystery to you, and you'll be frustrated. And so the easy way to avoid that is to just open with Notepad. Notepad is specifically for text files, and it just works best. Oops, too far. So we're back to one of these wire files, and the first step that you would do would be to update those 2 lines of text information. Now you get to what's really important. You have to update the cross-sectional area, the diameter, the unit weight, and the strength. And like I said before, you find those on the data sheet. Slightly different order, but you can see here the corresponding values. And then you should also update that maximum rated design tension that we're going to talk about more later. And different manufacturers are going to present the information slightly different, but it should all be there. And if not, of course, you can go back and ask them for what's missing. After you've updated the information, well, you then save that new wire file, you load it into PLS CAD, complete your problem file by adding in, checking all your loading conditions that we talked about earlier in the presentation, add your span information, and then let the program compute everything for you. Switching over to Southwire SAG-10 program, you set up a problem file, but as I say, a little bit different. First, you start with the cable data entry. The biggest difference is that Southwire SAG-10 program separates the cable data from the chart data. And whereas PLS CAD and the wire files, everything is in one file. So in Southwire, you got to go and edit the cable data. By default, the program only includes OPGW data for some other manufacturer. I think they're located in Botswana or something, but maybe you'll recognize them. But trust me, select OPGW, and then you can edit the cable, and then you can put in some other manufacturer, such as NCAB's information in there, including that chart number. The program should then marry up the chart number with the cable data. But if it doesn't have the chart number in it, you can add it. And the way you do that is you've got to get the chart coefficients from the manufacturer. And there is a chart explorer in there where you can add a new chart. And unfortunately, you got to type in all those numbers I showed you before. But the SAG-10 program does structure that process a bit, which helps you avoid making errors in the data entry. It's still tedious, but at least you're not likely or less likely to make a mistake. Now, excuse me. And then after you've got the chart and the cable data in there, you again would enter your loading criteria, and you would enter your span information and let the program calculate the sag and tension for you. Now, some tips. In an ideal world, you should also be checking the zero fiber strain margin. Now, we talked about that extensively in my 101 presentation. I'm just going to remind you here that this is the point where the fiber begins to see tension on a cable. Begins to see the tension that's on the cable. So for example, if a cable has a rated breaking strength of 10,000 pounds, and I tell you it has a zero fiber strain margin equal to 60% rated breaking strength, you know that the fibers are not experiencing any tension until the tension gets to 6,000 pounds, right? So to ensure long-term optical reliability, you want the fibers to not have any tension on them at a minimum under everyday conditions. In the last presentation, we talk about the risk under some loading conditions if there is tension and how that's a calculated risk in some cases. But under an everyday condition, you certainly don't want there to be tension on the fiber. So in an ideal world, you would check that. Everyday condition meaning like 60 degrees Fahrenheit, no ice, no wind, and that tension would be less than that. Now, a couple problems in the real world with that. One is that a lot of manufacturers don't put their zero fiber strain margin on their data sheet. So it's like you'd have to go and ask every single time. And in fact, if you were really astute, you would notice, secret thing here, it got left off my own data sheet for this particular cable that I picked. My mistake. So it's not always there. And in that real world, this is not usually a problem. So that's why you can kind of get away, not kind of get away, you can get away with not really checking it and worrying about it too much. The reason is that everyday tension is typically around 15% rated breaking strength, maybe plus or minus 5 or so. And the zero fiber strain margins of even some not so good quality cables are generally above that. So you don't see too many cables with zero fiber strain margin below 20% rated breaking strength is what I'm telling you. So you can get by with not checking it. In the real world, in Mike's ideal world, at least, I would check it. This tip is more significant. You really do need to check for aeolian vibration and include a limit for it. And by the way, this limit, what I'm about to tell you, is true for any metal cable. So any ACSR, conventional ground wire, doesn't matter. Under some loading conditions, the final tension at 60 degrees final every day, meaning no ice, no wind, can be above 20% rated breaking strength. Technically, that's okay for the cable, but making your cable vulnerable to aeolian vibration. You're like almost guaranteed to have problems with the aeolian vibration, which might not damage the cable itself. So for example, a 3/8" EHS cable is not going to be damaged by the aeolian vibration because the steel has a very high endurance limit, but it can damage the hardware and it can damage the pole line hardware as well. So you'll have aeolian vibration problems. It'll just take a different form than what you would see in the form of damaging the cable itself. So what you really need to do is to keep that 60 degrees Fahrenheit, unloaded tension, final, less than 20% rated breaking strength. And by the way, when you go to ask for a vibration protection plan from a good accessory supplier like Preform Line Products, if that tension is above 20%, they're going to significantly increase the number of dampers that they recommend you use, and specifically, they're going to double them. So you're likely to have vibration problems. You're going to have to buy extra vibration dampers. So why don't you just mitigate the problem and keep it under 20% rated breaking strength? Turns out that PLS CAD includes this limit already. You ought to verify that it's there. In SAG 10, though, you need to add it yourself. So 20% rated breaking strength at 60 degrees, final, unloaded, maximum. Next tip. Also, for any metallic cable, the maximum sustained tension should never exceed 80% rated breaking strength. Again, doesn't matter, 150-mile-an-hour wind, 5 inches of ice, whatever you're looking at, a sustained tension, how long is that? You could argue about that, but over any significant amount of time, you don't want the cable above that. There's a technical reason for that that's beyond the scope of today's presentation, and that's recognized by other technical bodies around the world and the cable vendors themselves. And so it's no surprise that this is included already in the NESC Rule 250 C and D limits. So they do use that. And that's already included in PLS CAD, but in SAG 10, again, you have to add it. Now, there's a critical final step that we're going to talk about. And remember, I said there are two things, if nothing else, you learn from this webinar, I want you to take away. And one of them is the importance of the cable's maximum rated design tension. And you got to check that yourself in both PLS CAD and SAG 10. Of course, the reason is that metal cables don't have an optical unit. So you kind of don't care. You can go up to that 80% limit and keep it there for 5 years and no problem. But with fiber optic cable, and specifically OPGW, if you go above the maximum rated design tension, that point is set to protect the optics. So if you exceed it, you risk damaging the optics in the cable. That could take the form of a short-term problem, right? You install the cable today, and tomorrow the fiber go dark or increased attenuation, or it might be something that happens in 5, 10, or 15 years. But either way, you risk optical problems if you exceed that. And by the way, if it happens in the short term, it's likely that the cable manufacturer is going to say, oh, sorry, you exceeded our maximum rated design tension, and so therefore the warranty is void. And then you're going to have a bad day. So you need to check that. And again, I can't overemphasize this point. The tension under any and all conditions must never, ever exceed the cable's maximum rated design tension. Please check it. Okay, next up, real links. Two things, maximum rated design tension and real links. The problem with real links OPGW is that the truth is manufacturing can't really begin until we've got the real links. So you can send me an order for 1 million feet of my OPGW and I'm going to be really happy at first. But there's not much I can do if you don't give me the real links with it. Now, I can order the fiber, but odds are I've already got fiber on hand anyway. I'm a fiber optic cable company. Of course I have fiber on hand. I might have some steel rod, or my wire vendor might have steel rod and aluminum. But at the end of the day, that too is something that probably already have on hand, don't have to order. And even if I do have to order those two things, they're generally not the critical path materials. Fiber you can get in a week or two, and steel rod and aluminum rod you can get in a week or two typically. The problem is that I have to begin making the optical unit. And the optical unit, whether it's a stainless steel tube or a plastic buffer tube, is always going to be made to specific lengths. And likewise, aluminum clad steel wire is made to specific lengths. And so I have to know your lengths in order to figure out what my lengths are going to be. And therefore, I'm at a standstill until I have your real lengths. And it's a constant source of kind of friction in our industry between customers and cable vendors. The quoted lead time is almost always based upon order and real links. So if I told you 10 to 12 weeks ARO after receipt of order and real links, if you place the order today and then don't get me the real links for 6 weeks, really, you're not getting your cable for 16 to 18 weeks, but then you're unhappy and you think that I I did something bad because you told me 10 to 12 weeks, but I'm going to say, well, you didn't give me your reel lengths. And then everybody has some friction. So I need for you to understand that this is critical. And the truth is, I really can't do much until I've got your reel lengths. Now, why are they so important with OPGW? You don't worry about it with ACSR as much. Well, it's because when an ACSR reel runs out, you have the option of just putting on a compression splice and keep pulling. But with OPGW, you've actually got to stop and put in a splice point and splice the fibers from reel 1 to reel 2 in order to keep going. So reel lengths become critical for OPGW. Now, I see two approaches to doing reel lengths in our industry. One is what's known as master or standard reel length. So some of our customers will order all the reels are the same. The general range is 18,000 to 25,000 feet. So I might have a customer that they place 100,000 feet order for OPGW, and I know that they always use 20,000 foot reels. So that's 5 reels, 20,000 feet. Great, I can get to work immediately. There are advantages to this approach. No engineering time to do that. So production begins immediately. You also don't have the possibility of reels getting mixed up in the field. That's also good. But the big disadvantage is more scrap. The other approach is specific or point-to-point reel length. So I go from tower number 1 to tower number 10, and then from tower number 10 to tower number 15. And maybe 1 to 10 is 10,000 feet, and 10 to 15 is 5,000 feet. And that's fine. Big advantage of that approach is that you don't scrap a lot of cable when you do that. But the disadvantages are that you've got to figure out those reel lengths, and that can delay production. And also there is the possibility that the crew could grab the wrong reel to string from tower 1 to 10 and leaving a problem later on. So either way, you've got to pick your splice points. And so now we're going to talk about that. Of course, the first thing is, what's a good location to set up to do your pull? Such a location has to have good access, and it has to be able to support the weight of the equipment that you're using, right? So if a pole is in the middle of a swamp or something, that could be a problem. You might want to pick a different location for the splice point. You also have to maintain the cable manufacturer's recommended horizontal to vertical distance ratio, and that's shown here. This is a 1-to-1, which you see here, but some suppliers require 1-to-3 or even 1-to-4. You have to check this. So if this tower is 100 feet, just to keep the math simple, if it's 1-to-1, this distance is 100 feet. But if it's 1-to-3, this distance becomes 300 feet, which is a football field. And that can have a significant impact on which locations you choose for a splice point. You have to be able to set up in that location. Other guidelines are, which structures do you actually use? I see some customers that try to coordinate their splice points with where they're dead ending their conductor. That's okay. There's nothing wrong with that. But a tangent structure for the phase conductors can still be a good dead end splice point for the OPGW. And then I like to take advantage of large angles when I'm helping customers do it, because angles can be a limitation on what you can pull through. And so I can take an angle out of the equation if I choose that structure as a splice point. Again, assuming I can meet my setup criteria there. Another factor that you have to include in planning is, what's the maximum reel length that you can get? Now that's a function of a lot of different things. And the bottom line is that you get that from the cable manufacturer. Should be on their data sheet. If not, you'll have to ask. Now, you need to be aware that it is possible that a cable supplier can provide a longer length than can be safely pulled in. That happened to a customer here in the United States. They bought 20,000 foot reels, and then the cable manufacturer told them pulling restrictions that basically limited them to something like, I don't know, 15,000 feet. And when challenged on it, the cable supplier said, well, you just asked if we could make it. You didn't ask what we could actually let you pull in. So you got to watch that. How do you know what's safe to pull in? Well, your main guideline is the maximum pulling tension. And good quality cable will be good for up to 20% rated breaking strength. And that's common across many OPGW manufacturers, the really good ones. And in fact, if it's less than that, that cable manufacturer is actually told you that he is making not just poor quality cable, but cable with a really low zero fiber strain margin, which means he's not done a good job of either designing or making his optical unit. So that should be a red flag if this condition is not met. The reason for this limit is not because you're concerned about damaging the cable. The reason is because you're concerned about elongating the cable during the stringing process, which in turn would mess up the sagging process. So if I stretch the cable too much during my pulling process, I'm not going to damage the optics. I'm not really physically damaging the cable. I'm just setting up a condition where I can either get the sag right, but the tension is wrong, and specifically it's higher than you designed it to be, or I can get the tension correct, but the sag is wrong, and specifically it's greater than what you designed it to be. So you need to ensure that this pulling tension is going to be less than this limit so that your design is installed the way it was designed. How do you estimate that pull-in tension? Well, IEEE 524 gives you some guidelines on that. Basically, the tension at the cable payoff is going to be about half the design tension at the 60 degrees final initial unloaded condition. If you take that tension and divide by 0.98 raised to the n, where n is the number of structure, you get a good estimate. And this is just kind of a field experience thing. What's the 0.98 mean? Well, that's an assumption about the friction that each stringing block is imparting in the cable as it goes through. So as an example, if you've got a 19,500 foot pole that's through 30 structures, and the cable rated breaking strength is 20,000 pounds, and your design tension is 3,000 pounds, then the maximum pull-in limit is 4,000 pounds, and your estimated maximum tension is going to work out to 2,700 pounds, which is less than that 4,000 pound limit at 20%, so you're okay. Usually it's around long pulls with a lot of structures is when this becomes a problem. Sometimes it can kick in at 25. More often it's above 30 structures, but it's not hard math. Now, in addition to that, you need to check the number of angles. Now, there's a lot of variation from one manufacturer to another on this. Some will just say you can pull through one large angle, and they might define that as 60 degrees. They might define that as 45 degrees. You'll have to check. Here are some guidelines that InCab uses for a center tube design with an aluminum-clad center stainless steel. What another cable company, the one I think I mentioned, I think they're in Botswana, they call their product Centracore. And that cable, or an aluminum pipe type cable with plastic buffer tubes, what that other supplier calls Alumicore, we limit that to 270 degrees total line angle change. So if you got 5 angles and they're 40 degrees each, that's 200 degrees total, you're okay. Of these angles, one of which can be greater than 90 degrees. For a fully stranded type cable, what we call a type S, with a stainless steel loose tube, you can go through at least 360 degrees, of which 2 can be greater than 90. When you're doing this calculation, you can ignore anything less than 5 degrees. And then as I write here, this is just a rough guideline. It should be kind of a trigger for you. in this sense, trigger in the sense of, you know, this is a more challenging pull and you should check with the manufacturer to verify that this pull is going to be okay. Now, once you set out your splice points, you need to translate those into specific reel lengths if you're using the point-to-point method. And so here's my recommended formula for that. Sum up those horizontal span lengths, add the height to the first and the last structure. Oops, I skipped a step. Add 1.5% for sag. That's plenty. I say generally, but I've never seen a situation where that wasn't enough. Add the height to the first and last structure. Add what your splicing crew wants, which is typically 100 feet at each end. And then add another 100 feet to reeve the bull wheels. And then this will give you plenty of cable, but you won't be scrapping a lot. You'll have enough wraps on the reel, not a complete layer, but some wraps on the reel to maintain control. And generally this works out to 3 to 5% extra. Now, I get some customers who ask or tell me, well, you know, I just add 10%. My opinion, that's way overkill. Of course, I like making cable and I sell more that way, but it is kind of overkill and you're wasting a lot of cable and, you know, I don't like a lot of waste. When you use just a percentage adder, you're also at the extremes, leaving yourself vulnerable to problems. A short run, you might not have enough cable, and then on a long pull, you're greatly increasing the amount of cable that you might waste. So like I say, this is a good formula. It's tried and tested for over 20 years. Okay. Last thing to talk about on your purchase order. To help things go smoothly, you really need to work with your purchasing agent to make sure that you're ordering what you thought you were ordering, what you want to order, the part number, the quantity, and the price are right. This is very basic, but just this week we've been dealing with a customer where we quoted them 2 cables. We got their purchase order. They put the description for cable number 1 and the price for cable number 2. So which do they really want? And it's taken us the better part of a week to get that figured out. Those reel lengths we talked about, that's important. They need to be on there if you can. This is now the year 2020. So each cable is going to go out with a test report on it. Again, every manufacturer is going to do that attached to each and every reel, but it's 2020. You can get an email copy of it or some other electronic version of the test report for reference. You just need to ask. The shipping location needs to be on there and who the point of contact is and their phone number or email or other contact information. And again, it's 2020, so if you've got a job site in the middle of nowhere, you can just give the GPS coordinates. Works fine. And then remember to plan for that lead time. 10 to 12 weeks is normal, but right now it's actually up because everybody's a little bit busy, so you need to be aware about that. And closing comment, we do have on our website our advanced cable engineering system for both OPGW and ADSS. There's a lot of information that'll help you learn more about cable and designing with it. So we'd encourage you to try it out. And thanks. And now it's a question time. And let's see if I can bring that back. More Q&A. Okay, here we go. Let's see, do we have questions? Okay, and in 2 different reels, what is the process for field cutting OPGW? I'm sorry, I don't understand the question. What is the maximum sum of angles that you recommend can be pulled through? That was one of my slides. Let's go back here. It's by cable design type. But remember, this is strictly for in-cab. Other suppliers are going to have different limits, but you should ask them and they'll give you something. Aha, somebody has explained that their question was, if you have a reel in the field that needs to be cut into two different reels, what's the process for field cutting OPGW? Really, any good cable cutter, you know, what they use for conductor is fine for field cutting. Now, the splice prep guys may grumble later, but the truth is when they start their job, they're going to cut off a few inches, maybe even a foot of cable before they get started anyway. So, you know, you're not going to get a nice clean cut in the field with a ratchet type cable cutter. It's going to crush the end, but it's not really going to cause a problem. Now, a related thing about that is, you know, do you need to protect the end of the cable? And then my answer is no, not really. Again, the splice prep guys are going to cut off a few feet, a few inches, or maybe a few feet of cable before they get started anyway. Water with today's water blocking technology is not going to migrate more than a couple inches into the cable. I mean, I suppose if you left the cable exposed for 10 years, maybe that would be different. But in normal work, that's not going to cause a problem. But if it makes you feel better, you know, you can just tape over the end with duct tape or electrical tape. That's no problem. Uh, would you recommend short lengths of cable for a proper, easy installation? Um, 20 to 20,000 feet is no problem. And you're eliminating splice points. You know, we do have some customers that like they use 7,000 foot reels, and maybe for them a 10,000 foot reel is long. You know, we don't mind, but there's no reason that you can't go 20, 25,000 feet. Now, above that, above about 20,000 feet, you do start to get concerned about the tension that we talked about before, because the structure count is naturally going to float up with that increased length. The longest length that I installed in my career was 31,000 feet, and it went fine. Um, so I'll say I'm kind of agnostic on the length of cable. Okay. Okay, and let's see. I went to chat. Now I need to go back to Q&A. Q&A. Oh, okay. Here we go. Um, the difference between someone is asking about the difference between the maximum rated design tension and the zero fiber strain margin. Okay, the maximum rated design tension is going to be greater or at worst equal to the zero fiber strain margin. So the zero fiber strain margin is the point that the fibers begin to see tension that's on the cable. Under maximum rated design, or the maximum rated design tension may allow some tension on the fibers and that's going to be a function of the cable design. Okay, let me talk about this. So since I'm on the screen where you see the design types, a stranded stainless steel loose tube cable is going to have a minimum, a zero fiber strain margin of 80%. If it's, you know, our cable, any good cable. And that's also going to be its maximum rated design tension, because remember the slide before where I said for any metal cable, that should be the maximum that you're at. So for that design type, the two are the same. So the tension isn't going above 80%, and the fibers are never seeing tension in that design. But center tube type designs are usually much smaller cable. Um, like anything, advantages and disadvantages. There are advantages that they're smaller, which is good when you're taking down a conventional ground wire like a 3/8 inch EHS or a 7 number 8 or whatever, and you're replacing it with an OPGW, but you don't want to do a lot of extra work upgrading your structures. So a center tube cable is inherently going to have a lower maximum rated design tension. And typically it's going to be around 50% rated breaking strength. So once the tension goes above that, the fibers are experiencing um, tension, the zero fiber strain margin is going to be around 50%, and then the maximum rated design tension is going to be 60%. So it's going to allow you to go up through the traditional NESC Rule 250B, the heavy, medium, light loading conditions, because that's defined at 60% as the limit. But the fiber will have a little bit of tension during the time that the tension in the cable has crossed that 50% mark. Does that make sense? So if the cable's RBS is 10,000 pounds, it's a center tube design. And I tell you the zero fiber strain margin is 50%. You know that when the tension is above 5,000 pounds, the fiber has some tension on it. Now you try to keep that strain on the fiber below 0.2%. That's sort of the ideal, not the ideal, the optimal limit published by fiber suppliers. Sometimes it can exceed that, but that's what you try to maintain. And then you allow the cable to go no more than 60%. So the two, sometimes they're similar with a stranded stainless steel loose tube cable, but for center tube cables, the maximum rated design tension is above the zero fiber strain margin, and also that's true for aluminum pipe type cables as well. Sorry, rambling answer there, but I hope I answered your question. Keep going. List of machine tools. I'm sorry, I kind of is shown as the per percent where the fiber picks up strain. For this window is really small for me and it's hard to read. Here we go. There we go. That's a lot better. Okay. Can you provide a list of machines and tools to execute the OPGW deployment? Yeah, but not during this webinar. Usually that's a function of your installation instructions, and what we could do is send you a copy of our installation instructions and then a general guideline for installing OPGW as well as other types of cables used by utilities is IEEE 524. A question, would you recommend testing each reel at the staging area before installation to see how there is a QC test report on each reel? So perhaps this is overkill. I think that customers should test their cable when they receive it. And of course, then after it's installed, especially if a contractor is involved. If a contractor is involved, they can argue that, well, you gave me the cable and something happened during transportation. I don't care that it was good when it left the factory because the supplier gave you this test report. Something happened during transportation. Of course, the truth is nothing can happen that wouldn't have some obvious sign of physical damage to the cable that would affect the optics. But you take that out of the equation if you do a test. The other thing that you can do as a utility that I see some other utilities do is to say that I've turned the reel over to you. I know it was good when I got it because I got the factory test report. If it's bad after you install it, you're still on the hook for it, but you declare that up front. You're giving them an incentive to follow the instructions of the manufacturer. And then secondly, you are um, encouraging them to do their own test before they put it up. Okay. Asked about installation manual. Yes, we and our competitors are going to have installation instructions. You just have to request a copy of them. Somebody is asking about, do you do an acceptance after splicing end to end? And yes, usually there's a lot of utilities will test each reel after it's installed and then test again the overall link. You can make an argument that you don't need to test each individual reel. You can just test the link. And I accept that you're kind of trading off the additional cost of testing each and every reel with the possibility of finding a problem and the overall link at the end. But if you find a problem with the overall link at the end, you're going to be able to pinpoint where it is. So I don't think that's a bad process.
Mike? Hey, Mike?
Yes. Yes.
You're answering all the questions I've already answered.
Aha.
I appreciate the con. I appreciate the reinforcement, but it's not showing you what I've already sent as an answer.
Now I'm having a hard time reading this, so now I understand. So is there anything new we need to cover? Countries with high
we've got one about the double dead end loop overs, and I said I couldn't answer that unless I looked exactly at the situation. And then somebody wants to know about how temperature affects the cable tension and potential problems.
Oh, okay. Double dead end loop overs, if I understand, like you're double deading and you're not putting in a splice point, and those are fine. You have to check the geometry of that situation though, because if the cable could be abrading against the structure as it makes that loop over, that's obviously not good. And so what you would want to do is use a downlead clamp to prevent the cable from just moving freely and abrading. And are they allowed on distribution due to the bending radius? In general, the bending shouldn't be a problem even on a distribution line. But yeah, it's something you'd have to check. Each cable vendor is going to have a recommended minimum bending radius, and as long as you don't violate their restriction, you're okay on that. Countries with high temperature, could it affect the pulling point? Usually manufacturers, they tell you that it's okay to install their cable between some low temperature. For OPGW, for us, I believe it's minus 30 C, and then a high temperature. It's for us, I think 50 C or something like that. So basically, yeah, it could affect it. I mean, if a cable manufacturer says my cable can't be installed above 40 degrees C, well then you can't install the cable above that. Other than that, it really wouldn't affect the pull. I would assume that in such countries you would set your sagging charts would factor in the higher temperatures, and so you just sag per the higher temperatures after you've pulled the cable in. So that's the only effect I can think of.
And then we have another question about what are the best practices for cable protection during transport?
Well, everybody's going to ship on a flatbed truck. And what we do is we chalk the reels with wood, and then we require that the truck driver use 2 chains on each reel. And so that's my answer. The reels should be double chained down to the flatbed, and the reels should also be chalked. And then maybe the question they're wondering, do the reels need to be tarped or covered? And my answer is no, that they don't. Wood reels or steel reels shouldn't um, need to be tarped. Okay.
That's
Any
all I
other?
see, Mike.
Okay. Any to add to that? Should there be specific information regarding this protection in the purchase order? Well, if a utility wants the reels tarp, then yeah, you should put that on. Um, do the okay, now I understand. So I don't think it's necessary to put that, double chain and chalk the reels on your purchase order. That's my opinion. Because usually shipping terms are that the title of the goods doesn't change hands until they arrive to you. So every cable vendor has an incentive to make sure that when the reels leave the factory that they're properly secured. And I believe my competitors are doing the same thing as I'm doing anyway. And if for some reason they don't arrive in good condition because they weren't properly secured, well, both the manufacturer and the trucking company have a big problem. So there is something of an incentive for them to do the right thing without you having to require it. Anything's, require anything special. Okay, I think we're done with questions. I appreciate everybody's time and attention. And I'm going to go ahead and end now, and there'll be a poll, and then look for the end of class test. Thanks again for your participation, and take care.